Hello. Let me briefly mention that in the previous lecture, we showed that if a polynomial has at least degree 2, and if it has a 0 inside the field f, the field of coefficients, then it cannot be irreducible. In fact, by the factor theorem, it has a factor of x minus a if a is a 0 of the polynomial. And the converse of this statement holds as soon as the degree is either 2 or 3. And we call this the degree 2 or 3 irreducibility criterion. After this, we focused on understanding whether or not a polynomial, a polynomial with rational coefficients has a 0 or not. We proved the rational root criterion. We used this to show that if a monic polynomial has a rational solution, then it should be an integer. Then this is used in order to show that if a monic integer polynomial does not have a 0 mod n, then it cannot have a 0 in Q. This kind of residue map implying a result for Q, sometimes we call it a local to global type of argument, type of result. There are many results of this type in algebra, and typically we start looking at the contrapositive. So we assume that the certain property holds good for Q, then try to deduce that that type of property holds for Z, and then we pass from Z to Z sub n. So sometimes in more advanced theorems, maybe Z is not good enough, and we allow certain prime factors to be in the denominator, but we don't get to that. So let's go back to what we want to do next. So what we want to show next is the fact that residue maps can also help us to determine irreducibility, not only whether or not a polynomial has 0, but also determine if a polynomial is irreducible. We call it the mod P criterion. I'm going to formulate a version of mod P criterion, and then later we will make it more precise. I mean, it is precise, but we will make it more general. Okay, so what is the statement? So suppose that I start with a monic integer polynomial. So f is a monic integer polynomial. And suppose that for some prime number p, when I look at f mod p, it is irreducible. If this happens, then automatically we can deduce that f is irreducible in the field, in the ring of polynomials with coefficients in rational numbers. So we go from this finite object of mod p numbers, so the coefficients belong to this finite ring, to the infinite ring of rational numbers. It's a pretty effective criterion if we get lucky. So if we actually manage to find a prime where f is irreducible mod p, then we can determine that f is irreducible in this Q bracket X. Again, as I've mentioned, the outline of the proof is that we will consider the contrapositive of this. That means we are going to assume the polynomial is not irreducible in Q bracket X. And then we try to get a result over Z. So we pass this kind of information from Q to Z. And then we apply the residue map and conclude the result over Z sub P. So meaning we want to show that in that case, when I look at the polynomial mod P, it cannot be irreducible. So similar to the 0 case, when we wanted to understand whether or not not having 0 in Z sub n implies having 0, not having 0 in Q. So there again, we had this type of argument. We said not having 0 in Q implies having 0 in Z, and then we deduced having 0 in Z sub n. The first step was essentially the rational root criterion. It was much more subtle than the second step. The same is true here. The first step is kind of the meat part of the argument, and that is where we need to prove Gauss's lemma, among other things. And so Gauss's lemma is kind of the key ingredient in this proof. But before we get to the proof of this statement, let's start with the subtle difference between irreducibility in Q bracket X versus irreducibility in Z bracket X. So let's start with one example which illustrates this difference pretty well. So if I look at the single monomial 2x, it's a degree 1 polynomial, and therefore in Q bracket X, it is automatically irreducible. We've discussed that a degree 1 polynomial with coefficients inside the field f is automatically irreducible in f bracket X. But if I consider 2x as a polynomial in Z bracket X, then it is not irreducible, simply because I'm writing it as 2 times x, and neither 2 nor x are units. Therefore, 2x is not irreducible in Z bracket X. So as you can see, there is this subtle difference between being irreducible in Q bracket X and Z bracket X. And the main issue is that the group of units of Z bracket X is very small. It's the same as the group of units of Z, which consists of only 2 elements, -1 and 1. In particular, 2 is not a unit inside this ring, where it is a unit in Q bracket X. So that's why in Q bracket X, I'm not going to get a non-trivial decomposition of 2x, because 2 is a unit. But in Z bracket X, both 2 and x are not units. So that's the big difference between them. And if you think about it, we can extend this and have a more general pattern. As soon as the greatest common divisor of all the coefficients of a non-constant polynomial, non-constant integer polynomial is not 1, I can repeat this argument. Essentially, I can factor out this greatest common divisor and write down my polynomial as a product of this integer, which is not plus minus 1, times a polynomial of degree at least 1. And neither of them are units inside Z bracket X. And therefore, such a polynomial cannot be irreducible in Z bracket X. But of course, in Q bracket X, it depends on so I can factor out this greatest common divisor, but that's a unit, I can throw it out. So the whole question of irreducibility and non-irreducibility in Q bracket X has nothing to do with the GCD of the coefficients, but over Z, there is a subtle difference between them. So that brings us to the definition of content of an integer polynomial. So what is content of a non-zero integer polynomial? So content of a non-zero integer polynomial is essentially the greatest common divisor of the coefficients of the polynomial. So the greatest common divisor of coefficients of the polynomial is called the content of the polynomial f. And in this course, we denote content of f by alpha of f. In literature, it's often denoted by C of f, but in this course, we used C sub n for the residue maps, and I want to avoid confusion between the content function and the residue map function. Okay, so in any case, so in this course, we are going to denote the content of f by alpha of f. For instance, if I look at the polynomial 2x squared plus 6x plus 3, then the GCD of 2, 6, and 3 is 1, and therefore the content of this polynomial is just 1. But when I look at content of 2x minus 4, then I have to look at the GCD of 2 and 4, and I end up getting 2. So the content of 2x minus 4 is 2, and the content of 2x squared plus 6 plus 6x plus 3 is 1. In general, whenever I give you a monic integer polynomial, because the leading coefficient is 1, the GCD of the coefficients is 1. And therefore, the content of a monic integer polynomial is always 1. Okay, so now let's see basic properties of content before we get to the reducibility properties and so on. Essentially, using basic properties of greatest common divisor, we can get to these properties for content of a polynomial. So suppose I give you a polynomial which is not 0 with integer coefficients, and I give you a non-zero integer, and let's recall that C sub n is the residue map, is modulo n residue map. But I have extended it from the ring of polynomials with integer coefficients to the ring of polynomials with coefficients inside the ring of integers mod n. So these are the settings. Now, what are the results? The content of a scalar multiple of f is absolute value of a times content of the old polynomial. So if I start with polynomial f, the content of af is absolute value of f, a times content of f. Now, the next thing is that if I tell you content of f is a number d, then that means d is a common divisor of all the coefficients. So that means I can divide all the coefficients by this common divisor and still get a polynomial with integer coefficients. So this will be still a polynomial with integer coefficients, and the content of this new polynomial is 1. Essentially, I've already factored out the greatest common divisor and divided by this, and that means that remaining coefficients cannot have a common divisor except 1. And the last thing is that if I tell you f mod n is 0, that happens precisely when all the coefficients are multiples of n, and that means n should divide the greatest common divisor of all the coefficients, which means n should divide the content of f, and vice versa. If n does divide the content of f, that means that n is a common divisor of all the coefficients, and in turn that means that all the coefficients mod n are going to be 0. Okay, let's quickly go over the proofs. Essentially, the first one, I'm multiplying all the coefficients, let's call them C sub i's, by a, and then I'm asking myself what is the GCD of these new numbers. And we know that greatest common divisor have this property that if all the numbers are multiplied by a, then the greatest common divisor is multiplied by the absolute value of a. Recall that by we are using this convention that the GCD of a bunch of integers is always non-negative. That's why we need this absolute value. Now, similarly, so if we want to show the second part relies on the fact that if GCD of the coefficients, let's call them C sub i's, is d, then when I divide C sub i's by this GCD, the resulting integers are going to be co-prime. The GCD of these fractions is going to be 1. Essentially, they cannot have more common factors, and because if they had, then the GCD would have been larger. And finally, if n is a common divisor of a bunch of numbers, then it should divide the greatest common divisor of those numbers. So these are the results that you've seen before. These are some basic properties of the GCD, and if using those, we get these basic properties for content of polynomials, integer polynomials. Now, a polynomial is called primitive if its content is 1. If it's an integer polynomial, a non-zero integer polynomial, and its content is 1. So if this is the case, we call it a primitive polynomial. Okay, now the next lemma it prepares us to extend the definition of content to polynomials with rational coefficients. But so it's a kind of preparation. It gives us a connection between an arbitrary non-zero integer polynomial and primitive polynomials. So if you think about it, by this property 2 of content, so this property, it tells me that when alpha of f is d, when I divide by that, I'm going to get a polynomial that is primitive because its content is 1. So this is a primitive polynomial. Okay, so it is primitive. That means if I call this guy f bar, then I can write down f as this polynomial times d, and d is the content of f. So overall, that means this discussion shows that every non-zero polynomial, every non-zero integer polynomial can be written as its content times a primitive polynomial. So we can always find a primitive polynomial, and it's unique. In fact, I can find a unique primitive polynomial such that f is its content times f bar. Okay, so that's essentially the second property of the content function. Now we are going to use this in order to extend the definition of content to polynomials with rational coefficients. For every polynomial with rational coefficients, every non-zero polynomial with rational coefficients, there is a unique positive rational number. So there exists a unique positive rational number that we are going to denote it by q, and a primitive polynomial. That one is also unique. So there exists a unique pair of positive rational number and primitive polynomial f bar, such that f is just q times f bar. So every non-zero polynomial with rational coefficients can be written in a unique way as a product of a positive rational number and a primitive polynomial. And because we have already discussed it for polynomials with integer coefficients, we can, in that case, we can choose q to be alpha of f, which is the content of f. Okay, so again, when f is an integer polynomial, we can choose q to be alpha of f, and because it's unique, that's the only choice that we can have. So we start with existence. So because we have already proved it for integer polynomials, our tool would be that first we go from q to z, and then we use our result over z. That means what? That means we can just clear the denominator. So suppose n is a common denominator for all the coefficients of f. And that means what? That means when I consider f tilde, and which is n times fx, I end up getting an integer polynomial which is not zero. For integer polynomials, I know that it can be written as its content times a primitive polynomial. So that means by the previous lemma, I do know that there exists a primitive polynomial f bar such that f tilde is just its content times f bar. But again, let's recall what f tilde was. F tilde was n times f. Now that means we showed that n times f for some positive integer n is alpha of f tilde times a primitive polynomial. Now dividing both sides by n, I deduce that f can be written as a positive rational number times a primitive polynomial. And that shows the existence. If I just set this positive rational number bq, that gives us the equation that we asked for. So this q and f bar is primitive, so they give us the pair of a positive rational number and a primitive polynomial that give us the desired equation. Now let's show, and again, let me reiterate that if f is an integer, if a non-zero integer polynomial, then we could have chosen q to be just alpha of f. In that case, n is just 1, f tilde is just f, so we could have chosen q to be just alpha of f. Okay, so now this was the existence part. we showed the existence of such a pair. Now I want to show the uniqueness part. Meaning, if I manage to find two positive integers, two positive rational numbers, Q1 and Q2, and two primitive polynomials, F1 bar and F2 bar, and if I happen to know that Q1 times F1 bar is the same as Q2 times F2 bar, then I should deduce that Q1 is Q2 and F1 bar is F2 bar. Okay, so again, our tool would be passing two integers. Because Q1 and Q2 are rational numbers, I can find a common denominator, and I can assume that Q1 is M1 divided by M, and Q2 is M2 divided by M2, M2 divided by M, the same denominator for some integers, positive integers, M1, M2, and M. Now, I use this equation and multiply both sides by the common denominator of Q1 and Q2 and deduce that M1 times F1 bar is the same as M2 times F2 bar. Now, we consider content of both sides. Notice that because we have this law that when I multiply a polynomial by a positive number, the content is multiplied by that, I can deduce that the content of M1 times F1 bar is the same as M1 times the content of F1 bar. And similarly, the content of M2 times F2 bar is the same as M2 times the content of F2 bar. But F1 bar and F2 bar, both of them are primitive polynomials. That means their content is indeed 1. So this is 1 because this is a primitive polynomial. This is also 1. So from here, I can deduce that M1 is indeed M2. Now that they are the same, I can put them back, cancel them out, and deduce that F1 bar is also equal to F2 bar. And notice that Q1 was M1 divided by M, and Q2 is M2 divided by M. Because M1 is the same as M2, I get equality. That shows the uniqueness. Okay, so this means for every non-zero polynomial with rational coefficients, I can find a unique positive rational number Q and a primitive polynomial F bar such that F is Q times F bar. And we also pointed out that this Q is the same as the content when F is an integer polynomial. So that means now I can extend the definition of content of polynomials from integer polynomials to polynomials with rational coefficients. And I'm going to call this Q, this unique Q that we got in the previous lemma, we call that one to be the content of the polynomial F. And we are going to again denote this by alpha of F. And as we have pointed out, it is compatible with what we had earlier for integer polynomials. Okay, so now what are the basic properties of this extended function? So does this share the same properties as before? One of them, in fact, is already the definition, meaning a Q is defined in a way that F can be written as the content times a primitive polynomial. And in fact, this is the unique way of writing F as a product of a positive rational number and a primitive polynomial. Okay, this is in fact part of the definition of content. Now, how about when I multiply a polynomial by A? Is the content multiplied by the absolute value of A? And the answer is yes. So let's go over the proof of this part. So I'm multiplying a polynomial with rational coefficients by a non-zero rational number A. And in that case, I want to show that the content is multiplied by the absolute value of A. So what does content of F mean? It means that F can be written as its content times some primitive polynomial. So this F bar is a primitive polynomial. Now I'm going to multiply both sides by A. So A times Fx is A times the content of f times this primitive polynomial. Now, if a is already positive, then a times the content of f is a positive rational number, and by the uniqueness of the content, we deduce that this number is indeed the content of a times f. But if a is negative, then I have to make it into a positive rational number. So that's why in either case I need to pick the absolute value of a and put the sign of a over here. But notice that when f is a primitive polynomial, when f bar is a primitive polynomial, so is its negative. So it doesn't change the factorization as much. And in either case, we deduce that the content of a times f is precisely absolute value of a times the content of f. Okay, so this means that these two important properties of content we can extend for content of polynomials with rational coefficients. Okay, how can this help us? How can we get irreducibility out of these things? So remember, we want to go from rational numbers to integers. And our main tool is Gauss's lemma. So there are two versions of it. There are two results. Both of them were proved by Gauss. In some books, the version 1 is called Gauss's lemma. In some books, the second one. The second result is an extension of the first one. But the proof of the second one uses the first one. I'm going to call both of them Gauss's lemma version 1 and version 2. So what is the result? The first version says that if I tell you that both f and g are primitive, then their product is primitive. Okay, so it's an interesting result. It says again, if the GCD of the coefficients of f is the same as the GCD of the coefficients of g, and both of them are 1, then the GCD of the coefficients of fg is also 1. Okay, let's see how the proof goes. It's a nice application of what we learn about ring of polynomials with coefficients inside the integral domains. Okay, so suppose to the contrary that the product is not primitive. This means that all the coefficients have a common factor, a non-trivial common factor. So that means in particular it has a prime factor. So suppose P is a prime factor of the content of the product. That means when I look at all the coefficients of the product mod P, I get 0. This means C sub P applied to the product, I get 0. Notice C sub P is a ring homomorphism. That means product of F mod P and G mod P is 0 in Z sub P bracket X. But notice Z sub P is a field and therefore it's an integral domain. And we show that if D is an integral domain, so is the ring of polynomials with coefficients in D. So this is an integral domain. Now in this integral domain, product of these two polynomials is the product of these two polynomials. Product of these two polynomials is 0. Because it's an integral domain, that implies one of them should be 0. So either this one is 0 or this one is 0. What does that mean? This means either P divides all the coefficients of F or P divides all the coefficients of G. That means either P divides the content of F or P divides the content of G, but we assumed F and G are primitive. So we get a contradiction. So this contradiction implies that FG should have been primitive, is primitive. Okay, now using this result, we can show the second version, which is much nicer in some sense. It essentially says the content function is multiplicative. What does that mean? This means if I tell you that f and g are two non-zero polynomials with rational coefficients, then the content of product is product of contents. Notice that in particular, if alpha of f and alpha of g, both of them are 1, we can deduce that alpha of fg is also 1, which means if f and g, both of them are primitive, then their product is also primitive. So the second version is definitely a generalization of the first one, but the point is that in the proof, we are going to use the first one, the first version. Okay, how does the proof go? So we go back and ask ourselves, what does content mean? Content means that I can find primitive binomials f bar and g bar such that f is its content times f bar and g is its content times g bar. Now I'm going to consider f times g. So f times g would be content of f times content of g times f bar times g bar. Now I'm going to consider content of both sides. Then content of fg is, you see here I am multiplying this polynomial by this positive rational number. And we discussed that content of a scalar multiple of a polynomial is, so again, content of a times h is the same as absolute value of a times content of h. So now alpha f times alpha g is a positive rational number, so I can take it out of content function. So this is the same as the number alpha f times alpha g. So essentially I'm taking this guy out. This is a positive number, I'm taking it out, times content of the polynomial inside. But now notice f bar and g bar, both of them are primitive, and therefore their product is primitive. And that means this content is 1. And we are left by the product of contents of f and g. So we get this beautiful results that content is a multiplicative function. Okay, but what does it have to do with irreducibility? So this is the key point. This helps us to go from ring of polynomials with coefficients in Q to ring of polynomials with coefficients in Z. What do I mean by that? Suppose I give you a primitive polynomial, and I tell you that I managed to decompose it as a product of polynomials, but unfortunately, I only know that these polynomials have coefficients in Q, have rational coefficients. Now I ask you, can I decompose f into polynomials? Can I write it as product of polynomials with integer coefficients? And the answer is yes. So, and what is responsible, what can help us to prove this result is Gauss's lemma. So let's go through the statement and the proof. So f is primitive. I've managed to write down f as product of g sub i's, where g sub i's have rational coefficients. Then, if I look at the primitive factor of g sub i's, meaning I can find these g sub I bars that are primitive, and g sub I is just its content times these g sub I bars. This is the unique primitive form of g sub I. If that is the case, then my polynomial f is nothing but the product of these primitive forms of g sub i's. Let's see why this is the case. In particular, as you can see here, I'm not changing the degree of g sub i's, and I'm writing f as a product of these polynomials with the same degrees as g sub i's, but this time they belong to the ring of integers. The coefficients belong to the ring of integers. Okay. So by the second version of Gauss's lemma, I know that the content of f, which is the same as content of the product of g sub i's, is product of content of g sub i's. So this means product of contents of g sub i's is just 1. Okay, let's have this in mind. Now let's go back and look at the product of the primitive parts. So when I look at the product of the primitive parts, each one of these primitive polynomials is the inverse of the content times g sub I, not g sub I bar. So here I made a mistake. Okay, that's correct. So it's the content of g sub I times g sub I. Now I can write it as product of the contents inverse times product of these primitive polynomials. But this product we just showed over here, we showed that this is 1. and therefore I can just ignore it, and I'm left with a product of g sub i's, but product of g sub i's is just f, and we get the desired result. So all of a sudden, having a factorization in q bracket x gives us a factorization in z bracket x with the same degrees. So this can help us to deduce that if I start with a primitive polynomial whose degree is positive, a positive degree primitive polynomial, then being irreducible in q bracket x is the same as being irreducible in z bracket x. Let me quickly recall that we started the whole discussion about content by pointing out the subtle difference between irreducibility in z bracket x and q bracket x. We said a polynomial like 2x is irreducible in q bracket x, but it is not irreducible in z bracket x. And we pointed out that the reason that we have that is because the content of that polynomial is not 1. This corollary says that that's the only issue. If I tell you content of polynomial is 1 and it has positive degree, that's enough to show that irreducibility doesn't change in q bracket x versus z bracket x. Okay, so that's a nice corollary that we can get. So if I tell you that f is primitive, then being irreducible in q bracket x is equivalent then to being irreducible in z bracket x. So these irreducibility properties hold for both sides. Okay, so now let's see why this is the case. Working with irreducibility condition is not that easy. It's better to use non-irreducibility. That's why we focus and show the counterpositive of this statement. So I'm going to assume that f is not irreducible in let's say q bracket x, and from there because it is positive degree, it cannot be a unit, I can deduce that I can write f as a product of two polynomials, two non-constant polynomials with rational coefficients. Now I'm going to use my theorem here. It says that when I look at the primitive form of g sub i's, I still get the same decomposition because f is primitive. Because f is primitive, knowing that f can be written as g1 times g2, when I look at the primitive forms of g sub i's that be denoted by g sub 1 bar and g sub 2 bar, then I get the same decomposition. I get that f is g sub 1 times g sub 2, and g sub i's have the same degree. In fact, each one of them is a scalar multiple of the all g sub I. So g sub I bar has the same degree, and therefore it has positive degree. So I'm writing f as a product of two non-constant polynomials in z bracket x, and therefore it cannot be irreducible. And that's exactly what we wanted to show. Now let's go the other way around. Suppose that f is not irreducible, but this time in z bracket x, and I want to deduce that it cannot be irreducible in q bracket x. Again, because it's a non-constant polynomial, it cannot be a unit, and it cannot be zero either. So that means not being irreducible is equivalent to saying that I can write it as product of two non-unit polynomials. So there are two non-unit polynomials, h1 and h2, integer polynomials. And remember, the units, the group of units of z bracket x has only two elements, plus minus 1. That means h sub i's are not plus or minus 1. And f is written as h1 times h2. Now, I want to say that degree of h sub i's cannot be 0. So suppose degree of one of them is 0, then what can we deduce? I want to reach to a contradiction, and then from there I want to deduce that degree of h sub i's are positive. If this is the case, because h sub i's are definitely non-zero and they are not units, I get that h sub i's, so I have to also include 0 over here. So I get that h sub i's are constants, integers, that are not 1, -1, or 0. That means the content of F cannot be 1 because it's a multiple of C. And C is neither 1 or -1 and so on. So that means alpha can, so therefore F cannot be a primitive binomial, and that's a contradiction. And so it contradicts F being primitive. Okay, so this means degree of A sub i's are at least 1. That means I've managed to write down F as a product of two polynomials, two non-constant polynomials in Q bracket X. A sub i's belong to Z bracket X, so definitely they belong to Q bracket X. And so F is not irreducible in Q bracket X. This finishes proof of this if and only if statement. Okay, so now we have all the needed ingredient in order to prove the mod P irreducibility criterion. Let me make it a bit slightly more general. So suppose that F is primitive. Of course, when F is a monic binomial, automatically it is primitive. So there is nothing, it is a genuine extension of the initial statement that I've written. So suppose F is primitive. And in addition, let's assume that P is a prime, which does not divide the leading coefficient of this binomial. So again, when F is monic, definitely no prime can divide 1, and therefore we have this condition for sure. So F is primitive, P is a prime number which does not divide the leading coefficient of F. Now I look at my polynomial mod P. Notice because P doesn't divide the leading coefficient, degree stays the same. So I look at that mod P. If this polynomial happens to be irreducible in Z sub P bracket X, then we can deduce F is irreducible in Q bracket X. So irreducibility mod P implies irreducibility in Q bracket X. So let's go through the proof. Suppose to the contrary, the steps we have mentioned already. So let's go through the argument. We are going to show the contrapositive statement. And that means I'm going to assume that F is not irreducible in Q bracket X. So I'm going to assume that it is not irreducible in Q bracket X. So either F is constant, or it can be written as a product of non-constant polynomials. So, or either it can be written as a product of positive degree polynomials. Now notice that C sub P is irreducible. That's the assumption. So I'm not going with contrapositive. I actually am proving it by the contrary assumption, by contradiction. So because C sub P is indeed irreducible in Z sub P bracket X, it cannot be constant. And therefore, F cannot be constant. Okay, so this means the first possibility is out of picture. So this is not possible. And that means we are writing F as a product of two non-constant polynomials with rational coefficients. Now again, we use the result that proved and deduced that F can be written as the product of the primitive forms of G sub i's. So there are these primitive polynomials that are essentially the primitive forms of G sub i's. That means I can write G sub I as its content times these primitive polynomials. And my polynomial F is precisely product of these primitive forms of G sub i's. And the degree of G sub I bar is the same as the degree of G sub I. Moreover, from this equation, I can deduce from here, I can deduce that the leading coefficient of F is the same as the product of the leading coefficients of G sub 1 bar and G sub 2 bar. Again, notice that Z is an integral domain. That's why we have this equality. But P doesn't divide the leading coefficient of F. That was our assumption. And because it's product of the leading coefficients of G sub 1 bar and G sub 2 bar, we deduce that P doesn't divide neither leading coefficient of G sub 1 nor leading coefficient of G sub 2. That means, again, when I look at G sub I bars and look at it mod P, the degree doesn't drop. So the degree of G sub I bar is the same as the degree of G sub I bar mod P. In particular, it's a positive degree polynomial. But this equality that we have, all the involved polynomials are integer polynomials. So I can look at the mod P. So I look at this guy mod P, and then mod P map is a ring homomorphism. All of a sudden, I'm writing F mod P as a product of two non-constant polynomials. Notice that G sub P is a field. So whenever I can write a polynomial with coefficients inside a field as a product of two non-constant polynomials, it cannot be irreducible. And that gives us the needed contradiction. So this finishes the proof of the mod P criterion. In the next lecture, we will see how we can use this. For now.